Hey guys, welcome to Calculus Day 8. We're going to be talking about composites and transformations, and not necessarily in that order. This will be our last day of material before we have our first quiz. This is mainly because, well, we're kind of reaching the end of the preliminary stuff. Now we're going to actually get into the first real little bits of calculus. We're going to talk limits, we're going to talk how to take a derivative. Like, the next few weeks are going to be different. It's going to be new material. And I know some of you guys are already like, please give me new stuff. I get that. I understand. It's coming. I have to make sure we go through some preliminary material first, because otherwise those people who didn't understand it before, I don't want to jump into the deep end when I don't know if you can swim in the shallows. Okay? And some people can jump in the deep end and be safe and fine and happy. Some will drown. And we don't want anybody to drown on my watch. So after Tuesday, tomorrow, we'll have our quiz tomorrow. After that, we'll start new material, which will be limits. We'll do probably a week and a half to maybe 2 weeks of that, and then we'll take a couple days to do derivatives, and we'll be finished. It's going to be an interesting time. This will be our last bit. As far as quizzes go, do note that the quiz will be open book, open note. It'll be available starting on Tuesday at noon, same as normal. And it will be due on Friday, like at our normal time, like a regular assignment. It will be selected problems from today's assignment, as well as from previous assignments, with a small tweak to it. Like, instead of being a 4, maybe a 5. Okay, very small changes. You'll see many of the same formulas. We just asked many different questions about it. So, like one of the problems from last time, where it said, "Hey, plug in f of 5," it might say plug in f of 6. Okay, it's not going to be a huge difference. It's just making sure that you understand the concept in different ways and all that stuff. So let's take a look today at some composites and some transformations. We're going to start with transformations. So let's take a look. To talk about transformations, I have drawn a very simple non-standard graph. This is a graph which is the following points: 1, 1, 2, 3, 4, 4, and 5, 6. Now when we talk about transformations, there are basic ones to talk about. So for this list, I'm going to note that in all of these, we're going to use the following notation: y equals f of x is the original function. Now, I want to note something real quick that we may never talk about again, and you may never talk about in any other classes. Remember, when you talk about an equation, the x value is the distance along the x-axis. So when we say x is 3, what we mean is we're looking at the place in the graph that is 3 units to the right. When we say x is negative 2, we're looking at the place in the graph where it is 2 units to the left. When we talk about f of x, this is the distance along the y. This is why f of x and y are considered to be interchangeable. It's because f of x means we're moving along the y-axis. And so if I say f of x equals 3, well, that means my y value on the axis is up 3. If I say f of x is equal to negative 2, then my y value on the axis would be at negative 2. Let's look at this. There are some really common transformations. In fact, there's actually a full list of them. I'm going to make the full list coming on the paper. And we're going to look and see at how we can take that list and look at this picture. So let's see our list. So here we go. First two transformations are very similar. I'll go ahead and put them all in, I guess. Okay, so let's look at this list. These are the most common transformations, and what I want to first point out is you can actually predict what they're going to do if you remember these two facts. Because if you look at it, in each case there's a c. Now c we're going to consider to be a number. Like you could think of c as 3. So this would be like f of x minus 3, or f of x plus 3, or f of x minus 3, f of x plus 3. And so this c is just a number. Well, if you look at what c is attached to, you can predict what it's going to do on the graph. So look here, the c is being subtracted from the x, just the x. It is x minus c. What that means is the x is the one that's being adjusted. The x is being adjusted, so it changes on the x-axis. That is why f of x minus c is a horizontal shift. To the right. So because the c is attached to directly to x, it means it affects things on the x-axis. That's why it's a horizontal shift. So it'll take this place and move everything either left or right. And that's what the plus does. So, if it's inside the function, it means it moves to the right or to the left, depending on whether it's positive or negative. Notice here how the c is outside of f. C is being attached to f of x. Remember, f of x is the y-axis. So here, instead of having a horizontal shift, it will have a vertical shift. In this case, the minus would be down, and the plus would be, of course, up. And so you can see how, because of where the c is located in the problem, how it affects differently, right? If the c is with the x directly, well, it's a horizontal shift. If the c is with the f of x, then it's a vertical shift. Now over here, notice how the negative sign is being plugged directly to the x value. So what that's going to do is that's going to flip on the x-axis. Which means that we take the x-axis and we flip around the x. So every x value is switched. I guess it's a terrible way to phrase this. I don't like that phrasing. The book is weird about this. What a negative inside does is it swaps x values. I like that. So what a negative x would do here is it take this 1, 1 and make it a negative 1, 1. It'd flip it over to the left-hand side. So it's swapping our x values, whereas the negative on the outside swaps y values. What I mean by swap is I invert from positive to negative or from negative to positive. And this one will swap origin, or rotate 180 degrees. These last two are all stretches. So this will be a stretch away from x-axis, and this will be a compression towards the x-axis. This is your master list of kind of how this function will interact and how it will work. Now what we can do here is we can actually use this to help predict what's going to happen to these graphs and these points in order to see kind of how they're going to interact with each other. Okay, to show how to do this, I'm going to use an old trick, an old mathematician's trick here. I'm going to use something that's see-through. In this case, a little plastic baggie. What I'm going to mark my points and my line onto my little plastic baggie to kind of showcase how this function is going to change over time and showcase all the different ways in which it can change. So let's look at some of these. If this is my function f of x, let's make the following change. Let's showcase what f of x plus 1 would look like. Well, since it is positive, that means it's going to move my graph to the left, and how much it moves to the left is the number. So it's going to take this graph, f of x plus 1 is going to take this graph and shift it 1 unit to the left. Which will look a little something like this. So notice it's the exact same graph, it's just got a horizontal shift. It's been shifted to the left. How do I know it's to the left? Because it is plus. How do I know how far it shifts? Because it is 1. Compare this instead to f of x minus 2. So I can shift that means, since it is minus, that means it's going to shift it to the right. And since it's 2, that means we go to the right 2, 1, 2. So it's the same basic graph, just shifted either to the right or to the left. And we'll do the same trick here in a little bit when we showcase a basic function, like a cube or a square. So let's keep going. What if I wanted to do something like, on the outside, f of x plus 4? So again, I can see that we have a positive value, which means it's going to go up, and that means it's going to go up in particular 4. So I take my function and it moves up 1, 2, 3, 4. This would be a new version of this graph. It's the same graph, just shifted. How much? 4. Which direction? Up. I can tell because of these two things. I see the plus, I see the 4, I see where it's located. That tells me how this graph is going to change. If it had said instead something like f of x minus 3, the original function is here, minus 3 on the outside would indicate we're doing a shift down 3 units. So 1, 2, and 3. Now, to showcase the other versions, it's helpful to come back here and note one other detail, where the origin is. So the origin in this graph is right here, indicated with a little plus sign. Why is that so important? Well, let's look at our other options. If we do f of negative x, f of negative x looks like this. It takes the entire function and it's going to swap x values, meaning x values that were positive, like 1, 2, 4, and 5, are going to become negative values. So negative 1, negative 2, negative 4, negative 5. The y's aren't going to change. So the new values will be points like negative 5, 6, negative 4, 4, negative 2, 3, negative 1, 1. And so what it does is it actually flips it to the left. So the origin stays in the same spot. And notice these new points would have new values. This one right here is at the point negative 1, 1. This one over here is in the negative 2, 3, negative 4, 4, negative 5, 6. And so it's the same basic graph. I'm sticking my fingers. It's the same basic graph. It's just been flipped along the axis. And so negative x on the inside flips left to right. I like the way that's written. I should have thought of that in the first place. That's good. So it flips left to right. Notice that it flips around the origin. So if something was already to the left of the origin, it will go to the right of the origin. If it was already on the right, it will go to the left. Compare this to negative f of x. So there's my graph. There's the origin, all lined up nice and pretty. What's f of negative x going to do? Well, it's going to flip it the other way. It's going to swap y values. So y values that used to be positive, like 1, 3, 4, and 6, are going to become negative. In other words, this is not going to be 1, 1. It's going to become 1, negative 1, 2, negative 3, 4, negative 4, 5, negative 6, or like this. So the origin hasn't changed. It's the new version of this picture, where we flipped it top to bottom. So So what's the double negative do? One on the inside, one on the outside. Well, it's going to flip it once left to right, and then it's going to flip it again up and down, which means it's going to look something like this. Which you notice just takes this thing and swings it around 180 degrees. Or it's also known as rotating around the origin. Now, I can't use this very well to do the stretches and compressions, but they will just cause it to pull away from the x-axis, meaning they will elongate everything up and down, or it'll cause it to shrink towards the axis, so compress. So I'm going to take this picture and compress it down. Okay? So, the next question becomes very quickly, what happens if there's more than one change? So what would the function look like if I did f of negative x plus 2? Well, you do it by order of operation, so inside has to happen first. So we take this function, the negative x would mean that we flop left to right. So we do left to right. And then it says plus 2. So then the plus 2 means we would go up 2. This is what our version of this graph would look like. Notice it has new point values. This corner point here is the point -1, +3. This next point would be -2, +5. And so you can see how you can use this to interpret how various functions will act and interact over time. The big detail here is knowing that all of these transformations can occur at any moment in time and be able to see how they fit together. Let's now look at, in my opinion, a better example. I like this method to teach my geometry students, but for calculus it's good to use technology, so let's take a look at a calculator doing this. Okay, here's Desmos. Notice we have a basic function x cubed. So this is going to be my f of x. So if I want to do the first change that we talked about, which was, let me make this a little clearer here. Let's do f of x plus 1, this first one here. What it's going to mean is I need to take my function, and inside the cube, I need to put plus 1. Notice how that took my graph and shifted it 1 unit to the left, which is exactly what the statement says. If the positive value is going to shift my graph 1 unit to the left. And so being inside the cube shifts left and right. And vice versa, if I go down here to the f of x minus 2, if I change it to minus 2, notice I shifted it 2 units to the right. The original is here in red, the blue version has been shifted. And note these two are the exact same, so never forget that. Whereas if I did this one, or if I said plus 4, the next one we have on our list, notice how I took that red graph and just moved it up 4 units. And basically copied the graph just after that, shift of 4 units up or down. And so this allows us to talk about functions in wholly and new, unique ways. Because we can apply the concepts of transformations that we have here without needing a function, right? If we look at this original picture, just very briefly, there's no function here. But we can still make all these changes just by knowing the properties, which is a big detail. These properties are designed to work both with a function and without a function. And so make sure you know both. Okay, let's look at the other two we have. What if I have a negative inside the function? Well, notice how it takes my function and it flips it left to right. So the function like this point here, which is at +1, +1, is now at -1, +1. It just flipped the x and y values. If I look at the point here, it was at 2, 8. Now it's at -2, 8. So the x's have swapped. What used to be positive is now negative. What used to be negative is now positive. Notice the y's didn't change though. So it's still 8 and 8. It's just whether the x is positive or negative. Here on the original it's +2. Now it's -2. On the original it was -1, -1. Now it's +1, -1. The x's have flip-flopped. If instead I put that negative on the outside, you can see in this example it looks exactly the same. But if I change over to a different example, like let's say x to the second, then this looks wildly different. This would become negative x to the second. And you can see for some graphs, the transformations look exactly the same. Some look different. For example, on this x squared version, if I put a negative on the inside, well, you can't see any change at all. That's because, though, 2, 4, if I flop the x value and get negative 2, positive 4, well, it's already on the graph. And this value, if I flopped it, it would just flop over here. So they flip-flop and they become the same thing. This is also referred to as reflexive, which we talked about, a week ago. The same basic concept. And then again, if I put a number out front, let's call it a. If that a is bigger than 1, what it will do is it will cause my graph to be pulled away from the axis. So you notice how you can keep track of your points. Like what used to be the point 2, 4 is now the point 2, like 7.1. The value of 2 has been pulled away to this new value. This is number right there. So instead of having 1, 1, it's now 1, 2. Instead of having 2, 4, it's now 2, 8. All the values have been pulled away from the x-axis. If I have it between 1 and 0, notice how it's to pull it towards. Let's see if I can get it a nice round number like a half. There we go. And so instead of having the point 1, 1 in my original graph, I have the point 1 and a half. Instead of having the point 2, 4 in my original graph, I have the point 2, 2. So it pulled it towards the axis. The x values didn't change, the y's did. So these are your basic transformations. And what you need to be able to do is you need to be able to do what we have in our problems from today. You need to be able to be given a picture like this one and say, okay, what will this thing look like? What will it look like if I take f of x plus 1? Well, it's going to take each of these points and move them to the left 1. What would I do if I had f of x minus 3? Well, it's going to take each of these points and move them all down 3. What if I had a composite of those? Well, then that would just make both changes in order. Now, speaking of which, the second part of today is a composite, and it's the last thing we talked about. What's a composite? A composite is when one function is substituted into another. To do this, I'm going to need to talk about two functions. I'm going to have f of x and g of x. F of x, I'm going to make a simple cubic function, like x cubed plus 4. And g of x, I'm going to make the square root of x minus 1. So, what's a composite? Well, there are a couple ways to write a composite. You can write f of g of x, or you can write f of g of x. What both these mean is you plug g into f. So in this example, f of g, which this is how that's read, f of g of x, would mean we take the f function, which is the cubed plus 4, and everywhere there used to be an x, we replace it with the g function. So this would be f of g of x. We take the f function, which is x cubed plus 4, and everywhere there used to be an x, we replace it with the g function. If I wanted to write g of f, we could also write it as g o f, because they're the same thing. And this means, plug f into g, which means we take the g function, which is the square root of x minus 1, and everywhere there used to be an x, we replace it with the f function, x cubed plus 4. And so this will generate a whole new function with wholly different properties, with a new domain, with a new range. Like, it's incredible what these composites can do. Now, a composite can do as many different things you want it to do. For example, you could do a composite of f of f. What that means is, this would be f of f. This just means plug f into f. So my f function, remember, is something cubed plus 4. So if I want to do f of f, I have to take that x cubed plus 4 and plug it into x cubed plus 4. And so this allows me to talk about more advanced functions by talking about them in very basic terms. And I could similarly do g of g. Now, what's the big detail about this that really matters? Well, what if I wanted to do something like f of g of 5? What this means is, in literal terms, it means take 5, plug into g, then plug into f. So it works from inside to outside. So plug 5. What this means is we're going to plug 5 into g. So g is the square root of 5 minus 1. And then plug that into the f function. So this is what f of g of 5 would look like. By comparison, if I wanted to do g of f of a number like, say, 1, what this would look like is we take 1, plug it into the f function, then plug that into the g function. And so it becomes order of operations very quickly. Let's actually solve a couple of these. So what if I asked you about, say, f of g of, 2? What this would mean is I can take 2 and plug it into g. So this would be the square root of 2 minus 1. The square root of 2 minus 1, well, 2 minus 1 is 1. The square root of 1 is 1. So f of g of 2 is equivalent to f of 1, because if I plug 2 into g, I get 1. And if I plug 1 into f, I get 5. And so f of g of 2 is just 5. I can either do it in pieces like I did here, or by doing it like we did up here, where we do the square root of 2 minus 1 cubed plus 4. Like, both ways will get me the same answer no matter how I do it. If I did something like g of f of, what's a good number here? Let's do 2. Why not? This means I would need to do g of plugging 2 into f. If I plug 2 into f, that'd be 2 cubed plus 4. 2 cubed is 8 plus 4, that would be 12. So g of f of 2 is equivalent to g of 12. It's just a g function evaluated when f is 2. G of 12 would just be, the square root of 12 minus 1. Square root of 12 minus 1 would be the square root of 11. Or I could do it by doing the square root of, 2 cubed plus 4 minus 1. All a composite does is everywhere there used to be an x, we replace it with an entire function. So doing one last example, if I have something like x squared plus 3x plus 2, right? Standard quadratic. If this is my f of x, and my g of x is, 6x plus 1. If I want to determine what f of g is, I just take my f function, everywhere there used to be an x, I plug in g. So that'd be 6x plus 1 squared plus 3, 6x plus 1 plus 2. If I wanted to do g of f, I take the g function, which is 6x plus 1, and everywhere there used to be an x, I replace with x squared plus 3x plus 2. And so these end up being entirely different functions and acting in entirely different ways. You need to be able to look at a function like this and be able to plug into both at the same time. It's an algebra skill that is very useful, and we will use this notation quite often in this class. So I hope you've seen it before and hope you're prepared to use it. That'll be it for today. Tomorrow I will release your quiz. Tonight's assignment is very short. That is because, well, there's not a lot of math here. It's a lot of understanding. The math is minimal. Like these two answers here, I'm fine with you leaving them right there. I'd be fine with you leaving it right here. Like, I'm fine with you leaving it in unsimplified form unless you're plugging in. Like, I'd be fine here. I'd want you to simplify this. I'd be fine here. I'd want you to simplify that. I'm fine here, but we have to get a number answer for these two. Okay? And some problems ask you to get a number answer. Some ask to get an equation. So know when to stop. But that'll be it. Remember, quiz tomorrow. Otherwise, happy Monday, and I will see you guys then.